And we're back. Hopefully it was only seconds for you. It was about 20 minutes for me, so that's so much fun. Alright, so we had the semicircle 1 on the last example, and we got this next one, part D, which is a little bit strange. Again, not something that I would really expect you to recognize coming into this class, because you don't really see functions like that very often in the past, or at all in the past. But after I kind of walk through it, hopefully going forward, we're going to be able to recognize them when they come up again. Before we actually get to this example D, let's go ahead and just look kind of more at just the general parent function. So if I have the absolute value of x over x, right? It's just like the one on D. This one just has a vertical stretch times 3, but we're just going to kind of ignore the little bit harder one. We're just going to work with the parent function right now, right? And let's see what type of a graph would this generate? What type of a function are we going to call this? Well, when in doubt, right, if you're trying to graph something, you can always just plug and chug. Pick an x value, plug it in, see what the output value is, plot the point, and then connect the dots to get the graph. So let's try this. Let's try like x equals 3. Right? If I plug in 3, I'd have the absolute value of 3 over 3. The absolute value of 3 is 3. Denominator still 3, which reduces to 1, right? So if I were to come over here to 3, the point would be up at 1. Let's try another one. Like how about x equals, let's say 7. So if I did the absolute value of 7 over 7, well, the absolute value of 7 is 7. The denominator is still 7. So look at that. That's also 1. So if I came over here to 7, that point would also be 1 unit on the y-axis. Let's try like one more positive. Like how about if I did x equals, how about 54? Just random number. Who cares? You'd have the absolute value of 54 over 54, you know, which would give you 54 over 54, which would give you 1, right? So for any positive value, whether that be 3 or 7 or 54 or any other positive number, when you plug in a positive number, the absolute value of a positive number is just going to give you that same positive number. So then you have some number on the top and that same corresponding matching number in the bottom, like 3 over 3 or 7 over 7 or 54 over 54, and that ratio is always going to give you 1. Right? So for any positive x value, the function is going to end up giving you an output of 1. Now you can't plug in 0, right? Because if you plug in 0, you're going to have a 0 in the denominator, so that one's not going to work. But for the domain, we'll say all real numbers, x can't be 0. And this one's going to have an empty dot right here. But for any positive input, your output is going to be 1. Let's check. Ooh, sorry, I guess. Okay, we'll just do it, and then I'll graph the other one with like a different color and pen. That's totally my bad. I guess we should eventually graph this. I'm graphing this one first. Oh well. Let's try a negative value. So how about if I plugged in, how about negative 5? Again, any negative number would work. But if I did the absolute value of negative 5 over negative 5, I know the denominator is still this exact same thing, but when I take the absolute value of the negative is going to go away. So when I plug in a negative input, I'm not going to end up getting out a positive one, right? The top is positive, but the bottom would be negative. When you plug in a positive, your output is a positive one, because both the bottom and the top, they're both positives. But if your input is negative, this negative in the denominator is going to end up making that overall output negative. And you could plug in any other negative number, like you could plug in negative 82. You'd have a positive 82 on the top, negative 82 on the bottom, which would end up giving you out a negative 1 overall. So I kind of like to call these step functions, because you've got this lower step, which for us, for the parent function, was down at negative 1, and then you've got the upper step, which is at a height of 1, right? So that's just the basic parent function. You have the upper step at 1. Remember, any positive input gives you an output of 1. Any negative x value gives you on the lower step an output of negative 1. Now let's actually go back, and here I'll graph this one in blue, so that maybe we can tell the difference. The only thing that this 3 is going to do is a vertical stretch, right? Remember your transformations. There's your parent function. If you have a scalar multiple to it, right, 3, it's just going to multiply it by 3. So instead of this top step being at 1, now that top step is going to be at 3, and then the bottom step would be at -3. Okay, so step functions, again, not something that you probably would have seen a whole lot, but hopefully they're not too bad. Remember, watch out for your shifts. If you have like an x minus 2 in the absolute values, and then you had an x minus 2, well then that would shift everything 2 units to the right. Or if you had an x plus 4, and then an x plus 4, then it would shift it 4 units to the left. So these step functions can shift also. If you had a plus 5 at the end, then everything would just shift up 5. If you had a minus 2 at the bottom, everything would shift down 2. So you can still have shifts as well, but this 3 is just a vertical stretch times 3, right? So step functions, anytime you see the absolute value on the top and just the x on the bottom, this is going to cancel, but it may cancel and give you out a positive ratio, or it may cancel and give you out this negative ratio. Now here's a little question. If I were to look at this instead, right? So here we had this as the parent function. If I were to look at this other one, would the graph be any different? The answer is no, right? For here, when you have the absolute value on top, the regular on the bottom, well, that's fine. Positive on top, positive on bottom, got 1. If I did the same thing, if I plugged in 3, you'd have a 3 on the top. The absolute value of 3 is 3, so you'd have a 3 on the bottom. You'd still end up getting a 1. And if I plugged in something like a -5, the only thing different, since those two are switched compared to the one we did earlier, the only thing different is that these two would be switched, but the output would still be -1. So this function and this function would both give you the exact same graph, right? It's that typical parent function for that step. Watch out. Steps can be shifted right, can be shifted left, can be shifted up or down, can be stretched, but they're really not too bad. And if you're ever in any doubt, just plug and chug. Plug in the next value, figure out the corresponding y, plot the point, and then connect them. All right, this one actually does not have any x-intercepts. There's no value that you can plug in that gives you out 0. Y-intercept, kind of the same thing. You can't plug in 0, right? This y-axis never has a solid dot in it. So that also has no y-intercept. Here the range, let's look again, the range for this one, the range would either be -1 or 1, right? You could write that as y equals -1 or y equals 1. I kind of like to write it, since there's only these two possible outputs, I'm going to write it in set notation. So for this, the outputs could potentially be -3, or they could be 3. And I'm going to write that in set notation, just collecting all the list, the entire list of all the possible outputs, just going to put them in these little curly brackets, right? There's other ways to write it, but I think that's kind of the easiest one. So watch out for the semicircles. Watch out for the steps. Those are things you probably wouldn't have seen coming in, but going forward, you need to know how to recognize it. All right, last one on this page is going to be a piecewise function. It's pretty easy. You just graph one piece at a time. So here we go. I've got a parabola shifted 1 unit down, and we're going to graph that everything looks like less than or equal to 0. I kind of like to do these dotted lines. It's going to help me see everything to the left of that. I'm going to graph this function. Then everything to the right of that, I'm going to graph the other one. So you just do one piece at a time. That's why it's called a piecewise function, right? You got multiple pieces. Anyways, that's a parabola shifted 1 unit down. 1 down. So that one should be pretty easy to shift. It's just going to go something like this. And then that part's all done. How wonderful. And you would want a solid dot, since it's less than or equal to 0. Solid dot on that kind of transitionary point. And then the next one, that's just a line. It has a slope of 1/3, and it's got a y-intercept of -2, right? Y equals mx plus b, so here's your y-intercept. It's down here at -2, which I'm going to put with an empty circle, an open dot, because it's non-inclusive, and then I'm going to have a slope of 1/3. So I'm going to go to up 1 over 3, up 1 over 3. So this is going to kind of go up slowly. It would go up 1, 1, 2, 3. then go up 1, 1, 2, 3. Oh, okay. Well, I kind of didn't get that super well. It would have an intercept over at 6, and if you're ever in any doubt, just set this thing equal to 0. 1/3 of x minus 2 equals to 0. Add the 2 over. X is going to be 6. Right. This one didn't even ask us for the intercepts, but if you wanted to, could have got them. So the piecewise function, pretty easy. You just graph one piece at a time. Got the parabola from the first part, and then you're going to end up having the linear function from the second part. You just connect them. Right, not too bad. Okay, let's try to get one of the rationals done before my time runs out on this video. Let's flip it over. Actually, you know what? I'm just going to pause this video, and we'll come back with the next one and finish off those two.